Protein systems do not fail all at once. They collapse in sequence: water first, then feed, then energy. Meat depends on every layer remaining intact. This food was built for the moment they don't. It produced protein in heat, drought, and isolation, long after livestock systems broke down. Modern diets didn't replace it. They removed it. The tepary bean is an arid zone legume developed under sustained water scarcity rather than controlled agricultural conditions. Research documented by the United States Department of Agriculture shows that it maintains protein production in extreme heat and drought where irrigated crops and livestock systems become unstable. Its relevance was not nutritional novelty, but functional reliability under constraint. As modern agriculture prioritized uniform yields, mechanization, and market scalability, crops optimized for failure-resistant performance lost institutional support and disappeared from diets. The tepary bean originates in the desert landscapes of the American Southwest and northern Mexico, where agriculture developed under permanent water scarcity rather than seasonal abundance. Long before irrigation infrastructure existed, indigenous farming systems selected crops that could survive heat, erratic rainfall, and shallow soils. The tepary bean emerged from this context as a deliberately chosen food, not an experimental one. According to documentation from the Smithsonian National Museum of the American Indian, tepary beans were cultivated by indigenous communities as a primary survival crop, valued for their reliability rather than their yield under ideal conditions. They were planted to mature quickly, withstand drought, and provide dependable protein when other foods failed. These beans were grown without irrigation, fertilizers, or external inputs, making them suited to environments where livestock and water-dependent crops could not be sustained. Because of this, the tepary bean was never treated as a commodity crop. It was embedded in local food systems designed around resilience, not trade. Its role was to prevent failure, not to maximize surplus. That origin defines why it still performs where modern food systems struggle. Protein production in modern diets is structured around animals. Feed crops are grown first, water is diverted to support them, and energy is consumed to convert plant calories into meat. This layered system functions only while every input remains stable. When any link weakens, protein availability drops rapidly. The tepary bean operates outside this structure. It produces protein directly from soil, sunlight, and limited rainfall, without passing through an animal system. There is no feed conversion loss, no dependency on grazing land, and no requirement for continuous water access. The protein yield is smaller in absolute terms, but far more reliable under constraint. This difference is structural, not ideological. Animal protein concentrates nutrition, but it also concentrates risk. Drought, heat, or feed disruption affects the entire system at once. The tepary bean spreads that risk across time and conditions, continuing to produce food even as surrounding systems fail. In environments defined by scarcity, reliability becomes more valuable than abundance. The tepary bean was never designed to compete with meat under ideal conditions. It was designed to replace it when those conditions disappear. Water scarcity is not a gradual pressure on food systems. It creates thresholds. Once crossed, yields do not decline slowly, they collapse. Most protein systems are built close to those limits. Livestock requires sustained water access not only for animals, but for feed crops grown elsewhere. When drought intensifies, failure is rapid and widespread. The tepary bean was developed beyond that threshold. According to assessments published by the Food and Agriculture Organization of the United Nations, tepary beans are among the most drought-tolerant legumes ever domesticated, capable of producing grain under rainfall levels that cause other crops to fail entirely. Their growth cycle aligns with short, unpredictable rain events rather than seasonal stability. This tolerance changes the risk profile of protein production. Instead of depending on consistent water delivery, tepary beans exploit brief moisture windows and complete development before heat stress peaks. Yield may vary, but total failure is rare. In scarcity-driven environments, avoiding collapse matters more than maximizing output. This is why the tepary bean functioned as insurance rather than surplus. It reduced the probability of protein loss when water systems broke down, a role modern agriculture no longer measures. Protein availability is shaped as much by storage as by production. Meat depends on continuous refrigeration, rapid transport, and uninterrupted energy supply. Once any of these systems fail, large portions of protein are lost within days. In scarcity conditions, perishability becomes a structural weakness rather than a logistical inconvenience. The tepary bean operates under a different logic. When dried, it can be stored for years without refrigeration, preservatives, or energy inputs. Transport does not require cold chains, and losses during distribution remain minimal. This stability allows protein to be accumulated gradually and used when production is no longer possible. In historical food systems, this mattered more than volume. Stored protein functioned as a buffer against drought, heat waves, and seasonal gaps. The ability to hold food through disruption determined survival outcomes long before yield statistics existed. Modern systems optimized for speed and freshness rather than endurance. As a result, foods that could tolerate interruption lost relevance. The tepary bean did not disappear because it spoiled. It disappeared because the systems built around it were no longer valued. Modern agriculture evaluates crops by metrics tied to scale, uniformity, and market integration rather than environmental resilience. Systems structured around irrigation networks, mechanized planting, and global supply chains are optimized for a narrow set of major commodities with predictable outputs and centralized distribution. In contrast, crops adapted to extreme environments, like the tepary bean, rarely fit these efficiency paradigms, making them less attractive to research, policy, and investment. The tepary bean is categorized among the world's neglected and underutilized crops, a group that includes domesticated plant species historically important in local diets, but not incorporated into mainstream agriculture or global markets. These crops have seen production decline not because they lack nutritional or ecological value, but because their traits are not aligned with standardized commodity systems. Their underuse reflects systemic biases in agricultural research, breeding, and policy that favor a limited set of high-input, high-export crops at the expense of biodiversity and food system resilience. The tepary bean did not disappear because it failed to perform. It continued to grow in arid regions long after it was abandoned by large-scale agriculture. What changed was not the plant, but the structure of food systems around it. As diets became centralized and protein production shifted toward industrial livestock, local crops lost their strategic value. Protein was no longer defined by reliability under stress. It became defined by consistency, volume, and market throughput. Foods that operated outside refrigeration, feed markets, and transport infrastructure were no longer prioritized. The tepary bean did not align with these systems, and so it was gradually removed from research agendas, extension programs, and public awareness. This removal was cultural as much as economic. Knowledge of how to grow, cook, and value the tepary bean declined as imported foods replaced local staples. What remained was the assumption that its absence reflected inferiority. In reality, it reflected a shift in what modern food systems chose to measure. The tepary bean was not displaced by something more resilient. It was displaced by systems that no longer planned for failure. Resource limits are no longer hypothetical. Water scarcity, heat stress, and energy volatility are already shaping how food systems perform. Protein production is often the first pressure point because it depends on multiple inputs remaining stable at the same time. When those inputs weaken, failure is no longer gradual. It is sudden. The tepary bean matters because it represents a protein strategy built outside those dependencies. It does not require feed crops, irrigation infrastructure, refrigeration, or long transport chains to function. Its value is not in replacing modern protein systems during abundance, but in sustaining nutrition when those systems falter. As climate instability increases, the distinction between efficiency and resilience becomes critical. Foods optimized for ideal conditions perform poorly when variability increases. Foods designed for constraint remain usable. The tepary bean belongs to the second category. This comparison is not about returning to the past. It is about understanding which food systems were built to survive disruption, and why they were removed when disruption was no longer planned for. Some foods were never meant to dominate markets or supply chains. They were meant to prevent failure. The tepary bean was one of them. It produced protein under conditions where water was scarce, heat was constant, and infrastructure could not be relied on. Modern food systems replaced that logic with efficiency and scale, assuming stability would always hold. It doesn't. As resource limits return, the question is no longer which foods perform best in ideal conditions, but which ones continue to function when systems break. For more overlooked food systems and forgotten agricultural logic, subscribe to Nutrient Relics.